Let's do another LeetCode. We are now at 10%. Next one is a hard problem. I managed to solve the last hard problem, so now I'm feeling very hopeful. We'll see. Alright. I've forgotten to start timer every single time. Let's do this. If I cannot solve this within an hour, then I will give up and just learn from other people's solutions. Trapping rainwater. This actually looks a little bit familiar. Maybe LeetCode had some other similar questions, I feel like. Although I have not solved this one or seen it before. Okay, height 0, 1, 0, 2, 1, 0, 1, 3, 2, 1, 2, 1. Oh, I see. So that's the trapped water. That's volume 1, volume 1, volume 4. Because width is 1, and then these are also 1 unit. Alright. Interesting problem. What about this? How can we visualize this one? Well, at least we know 4 and 2. That will be trapping 2 volume. 0. No. That's not how it works. I will need to actually draw this. How can I show it here? Let's see. 4. Okay, 4. 2. 0. And we have 3. 4, 2, 0. Okay, so that's this is we need some kind of index. Okay. So 4, 2, 0, 3, 2, and then 5. Okay, 4, 2, 0, 3, 2, 5. Between each of them, it's 1 unit width. So how much water would we have in this case? So this entire, I guess in this case, this entire area will be water. So all of this would be water, right? Yeah, so that will be 2 units, 4, 6, 7, 8, 9. Yeah, that's correct. Okay, that's good. Well, obviously we can calculate it once we draw it in front of our eyes, but what are the rules without seeing this graph? Okay, so we see here for 102, 102, that's like its own little area. It's only got this area. Nothing else will affect this because there's nothing here. And whatever that happens there will not affect it, and the water it can hold will depend on the lower edge. And same thing here. I'm thinking about something like a local peak. So this is a local peak. So we have this little local peak here. That's why this is separating the rainwater trapped there and the rainwater trapped on the other side. So that is a local peak, and we can get as much water as the lowest allows us. Now this is another local peak, and that's the amount of water we can get. Well, if we look at this, can we consider this one to be a local peak? It obviously doesn't work that way. Because there is a higher wall on the other side. Okay, so this doesn't have a higher wall on the other side, and this doesn't have a higher wall on the other side, so that's why it's segregated. Okay. Well, we need to come up with a systematic way to calculate this. Wow, this is so hard. Can't think of anything yet. And it's already been 9 minutes. Okay. Okay, so well, if we start at 0, we can ignore that because nothing's gonna happen with that. Okay, then we have 1, and if the next element is higher, then actually nothing will happen either. And if it is lower, then okay, so this is 2 units lower, this is 1 unit lower, so these 2 units will be trapped water only if there is a higher wall on the other side, no matter where it is. It has to be a higher wall, or at least equally high. Okay, so what if we think this way? Does this have an equally high or higher wall to the right? Yes, then this will be trapped water. And we do find once we encounter that higher wall, it's that little section is over. Then we can start over again. We have this, it's lower. If it's higher, then nothing happens. Then we just skip to the next. And then until it starts going lower, then we know that this will be trapped water, this will be trapped water, this will be trapped water, only when there's another wall. Well, it could also be the case that this one is 3. So this one was this high, and this one was 2 this high. So how it can go depends on the minimum of those 2 walls. Okay, so that would be that case. Okay, so this is good. This is having a taller wall on the right, having a taller wall on the right, and not having a taller wall on the right. So, okay, so for these cases, we know how to handle them. Now we are here. We're going downwards, and if we had a taller wall on the right, we would have filled this as well, but we don't. So what if we did something like this? So we go from left to right, and we do something like, we start from this wall, we find the equally or taller wall. To calculate how much water is here. Then we do the same. We are on this wall, we find the next equal or taller wall to calculate this part. And now we are here, we do not find any equal or taller wall, so nothing happens. And then we go from right to left and do the same thing. So we are here, we find that wall, we can calculate that. We're here, we do not find a taller wall, so there's nothing. Then we sum this up. Well, what would that be for this example? So we're here, taller wall is there, so that's it. Let's try this. This is my current thinking. So left to right, traversal. And we need how much water? Let's limit volume. Okay, we need to go over each element. So this is the left wall. Let's start the left wall with the first element. Okay, well, okay, so if we go over this, okay, let's ignore the first 0 elements and see if, let's write this part of the algorithm and see if the 0 element fits there anyways. So if we're here, I is 1, what do we want? We want to traverse until we find the equal or higher wall. The first one, not the rest of it, just the first one. Okay, so just the first one. If height is lower than height left, so if current wall is lower than the left wall, we wanna start calculating the volume. Well, in this case, that is lower, but we do not want to calculate that volume because we do not have a higher wall. So we need a temporary, just a temporary volume here. So let me just call this section because that's what I was referring to, this, the volume of that little section. So we start the section with 0 and we want to add up the difference. If height is smaller, left and current, okay. Else, otherwise it's the same or higher. So we added this part, now we're standing here and it's same or higher. So what do we do? That's the end of this little segment. I think that's when we can add in this little section to the total volume. And what else do we need? Oh, we can, this needs to be outside. Let's reset the section. And now we are okay. So when we are here, we adding this little volume and we reset the section to 0. Now the next round, it's gonna add this, then it goes and it's gonna add this, then it goes adding this, and then we are here, we'll be adding this section to volume and reset the section. And now we're here, we will be okay. One sec, someone's here. Let me just be back in a few seconds. Okay, so while we are standing here, next one, it's smaller, so it is adding this, it is adding that, it's adding that, it's adding that, but it's never gonna be added to the total volume because there's not a equal or higher wall on the right side. So that's what I'm thinking. And now we do this to do the same thing for the right side. Right to left traversal. Okay, let's just name it like this. Oh, what happened here? So now we're going from the last one until the first one. If height is smaller, so essentially we don't need to start from this. Maybe we can, maybe let's just start from the last. Well, it will be indexed out of range if we get a really small input. Okay, let's skip that for now. Okay, so when we're here, well, we start from this and we're starting from this again, so that's just the same. So it's just gonna be 0, adding 0. Okay, next. Okay, so that is higher. So nothing happens. Now this is Oh, very crucial part missed here. So when we are done with this little section, we are adding this volume to the total volume. We reset the volume, and we also need to reset the wall. Okay, so here this is higher, which means we will be done with this section. We will add that to the total volume. We reset the volume, and we need to reset the wall to the current height. So now the right wall is this one. That's what we compare with. So next round, it is smaller than the right wall, so we will calculate this unit in our volume section. And the next one is equal. So this little section will be added into volume, and this is the new wall. Next wall is higher, so nothing happens. This is the new wall, and then we have smaller, so this will be calculating all this, but we will never have a higher wall again on the left side, so that will not add into the total volume. Alright, so that is my current algorithm. It would be really cool if this works. Let's see. Wrong answer. What a bummer. Let's see why it's not working as I'm imagining. Let's print. Let's print. Okay, let's try that. Let's see if this one little left loop is working well. Okay. If height 0, it's the same. I see. So when we are here, left wall is now at index 3. We have volume 1. Then the next round we have height. Oh, I see. Oh, that's the problem. So left is just supposed to be. Oh, okay. Either left can be the wall height, or it could be just the index. So that's using the index, and now I'm updating the index. Same thing down here. Let's just use the index, right? So case 2 is good, but not case 1. Alright, let's see. Section complete current volume 0, it's at index 0. Okay, we're at index 1, current volume 1. Next wall is, left wall is not at index 3, current volume is 1. Then left, section left 1, 3, 4. Height left, height I, when we are here, now when we're at index 4, oh no, okay. Right. Okay, now that's doing what I'm designing it to do, at least. Let's see. Okay, past half of them. Output 4202. So that would just be 2, but I'm calculating 4 because current volume 0, left wall is at okay. Let me turn off my phone. Left wall is now at index 2. Oh, I see, because I double counted one is the same. So okay, so no double counting. Else if wait, okay. If the height is the same, then we just continue. Oh my god, I cannot believe it. Okay, I solved it and it's efficient. It's only like 34 minutes. That's really good. Oh, this is so exciting. I'm trying to be quiet, but I'm so excited that this is a hard problem. Okay, that's not bad. Let's have a look and just go over the solution one more time. So this is the total volume of how much trapped rainwater there will be. So we do one traversal left to right and then one right to left. So it's the same logic. So when we're doing left to right, what we are doing is we are always marking the left wall and then traversing until we find a wall that's equal or taller, because then we know that is where we trap the water. And once we find that, that little segment is done, because it wouldn't matter if, let's say this next one is this tall, it wouldn't matter because it will still only trap that little much water. It depends on the lower one. So once we find a wall that's equal or taller, we know that is done for that section. Then we just restart the left wall again and go until we find the next wall that's equal or taller. And while we're doing this, we're gonna calculate how much trapped water it is, and when we do find that equal or taller wall, we're gonna add that to the total volume. But in this case, when we do not find that taller wall, then nothing is added, and that's why we need to do it right to left again to do the reversal. So that would be added and the rest of it will not. So that's the algorithm. Okay, let's now do time and space analysis. So let's see, time, we have constant. This is a for loop that traverses the input once, so that's linear. Same thing here, so it's linear in time, and we are using just a few variables, no data structures. So linear time, constant space, that is usually the optimal. Okay, now we have some time to just look at the top solution anyways. Okay, so this is doing the traversal from like going this direction and that direction at the same time. If left side is lower, then we are gonna compare that to the tallest left wall. If it's taller, then we put that to be the tallest wall. Otherwise, we will calculate the volume. Okay, I think I need to visualize this in a concrete example to see that it actually works. Oh, okay. Okay, I need to drink some water. So this is my solution anyways. I will look at this later. I think that's it for this one. I'm glad I was able to solve this. So I will see you in the next one. And this is very efficient. Both times it was pretty efficient. Oh, especially this one I took away the print. Apparently this printing is taking so much time and space. Alright, see you next time.